Welcome back to Physics 152 Online. We'll finish this section on capacitors by considering what happens if we fill up the space between the capacitor plates by an insulating material. And when we do this, the whole purpose of that is to increase the capacitance. So when we fill up the space between the two capacitor plates with an insulating material, and it's also called a dielectric for reasons that will become clear in a moment, it generally increases the capacitance. But how does it work? What does the dielectric do? And we can understand this in a very cartoonish fashion by imagining that a dielectric has in it polar molecules which, unless they're subject to an external field, are generally random in their orientation. So in this sketch, consider each of these football-shaped objects as a dipole that has a positive and a negative end, but you can see initially they're randomly oriented. And now if we put this dielectric material in between the plates of a capacitor that's been charged up, there's an electric field between those plates. And so that electric field, as we saw earlier in the semester, exerts a torque on dipoles that tends to rotate them so that their positive ends line up pointing in the direction of the electric field. So the dipole moment rotates to line up with the applied electric field E0 here in this sketch. This shows what might be happening partially along the way to having those molecules lined up perfectly with the applied field. So as the applied field increases in strength, the alignment of these materials, these internal dipoles, gets greater. And so in an ideal situation, those dipoles might line up all together pointing so that their dipole moments are parallel to the applied electric field. So notice what that does though, okay? In the interior of the dielectric material, the plus and the minus signs cancel each other out. But on the far right-hand end in this sketch, there will be a layer of positive charge, and on the far left-hand end there will be a layer of negative charge. Now what does that do? The applied field was to the right, that's the E0, but notice this layer of positive charge on the right side of the dielectric and the negative charge on the left side, that produces a field pointing opposite to the externally applied field. And so we call that the induced field, and it lines up to oppose the applied field. So when you have an empty capacitor, the electric field inside would be E0. But when there's a dielectric, this induced field opposes it, and therefore the net field is less than E0. And so the presence of a dielectric reduces the electric field that would otherwise be present in between the capacitor plates. And we use a quantity called the dielectric constant, which is either indicated by K or kappa, to tell how significant that reduction is. So here's an empty capacitor. Imagine that we've got it charged up plus and minus Q using a potential difference V0 so that there's an electric field E0 in that empty capacitor, and its capacitance is Q over V0. Now if we fill it up with a dielectric that has a dielectric constant kappa, and when it's completely filled, these equations only work if that whole region in between the plates is completely filled, the electric field is reduced, and the factor of reduction is the dielectric constant kappa. And since electric field and voltage are proportional to one another, the voltage is also reduced. The potential difference is also reduced. So if we look at the definition of capacitance, C equals Q over V, the V that we now have is V naught over K, which means there's a factor of kappa in the numerator. So the new capacitance of the filled capacitor is kappa times the capacitance of the empty capacitor. And again, this only works if the dielectric completely fills the space. If the dielectric doesn't completely fill the space, then we would have to calculate the potential difference that goes into the denominator of the capacitance equation all the way across, and it would not be simply V0 over kappa. There would be a more complicated expression. So that's how dielectrics work. And there's also another phenomenon that happens quite often. It's called dielectric breakdown that we should take into account. If a capacitor has vacuum in between the positive and negative plates, then there's no way for charges to jump between them. But even if all we have is air in between them, then there is a possibility for what's called dielectric breakdown. If the charges that are built up on the capacitor plates jump from one to the other, then it destroys the it makes the stored energy and the stored charge go to zero. The capacitor gets discharged, and generally when this happens internal to the capacitor itself, it destroys the capacitor. And if you've got a dielectric material in there, then it usually burns a hole through it when that charge gets transferred from one plate to the other. And the measurement of the maximum electric field that a capacitor can sustain, or that its dielectric material can sustain, is called the dielectric strength. And so notice it is an electric field that we refer to as the dielectric strength. So even in air, there's a maximum electric field, and for air the approximate value is 3 kilovolts per millimeter, although it will depend on the pressure and the humidity of the air. So when you touch a doorknob, you feel it spark. You've had that familiar experience. What's happened is the electric field between your fingers and the doorknob has exceeded this dielectric strength of the air. And here's a quick example, similar to one of the problems that you'll have for homework. If you've got a parallel plate capacitor with a certain plate separation, and it's filled with polystyrene, which is a polymer film of the same thickness, find the maximum voltage that you can use to charge up the capacitor. And of course that will determine the maximum charge and therefore the maximum energy that you can store with the capacitor. You'll notice if you actually look at real-world capacitors that they often tell you what the maximum voltage is or what the maximum energy storage is for that device. So to answer this question, all we need to do is look up the values for polystyrene, and so I found kappa for polystyrene is 2.55 and the dielectric strength is 24 kilovolts per millimeter. So we want to now connect this quantity to the electric potential that you would have when the electric field would be 24 kilovolts per millimeter. So delta V is defined as minus integral E dot dl in between the plates of a capacitor. If we just take a simple path from one plate to the other along the field direction, then E dot dl becomes E times dl. In that geometry, it's a good approximation to state that the electric field has a constant magnitude in between the plates, so it comes outside, and we find, as we know for a uniform electric field, that the potential difference is simply minus the electric field magnitude times the distance. So if we sub in E equals E max, we can solve for delta V max. We know what D is, and so 24 kilovolts per millimeter times half a millimeter is 12 kilovolts. So according to the properties of polystyrene, for this plate separation, the maximum voltage that we could use to charge it up would be 12 kilovolts per millimeter. Any more than that, and we would exceed the dielectric strength and would expect to have dielectric breakdown, which will destroy the capacitor. Okay, that finishes our introductory study of capacitors, and I will see you in class.